liquid hydrogen cylinder, and the liquid hydrogen was heated in this reactor core, and it was exited by the nozzle so that we can get the desired thrust. But there were a few problems with these kind of structures, like we need to carry liquid hydrogen with us for propelling our nuclear powered assemblies of engines. These engines had already been tested in between 1915 to 1917. This is a list of few nuclear power engines which had given us successful testing, but due to international treaties came into effect in early 1970, we had to stop testing such engines. Like there was PV B4E, power generated by this engine was 937 megawatts, and we had operated it. World has operated it for 8 minutes at full power. And like Phoebus was also there. We had operated it for 5,000 megawatts, operated it 12 minutes, including a restart, because restart is a critical phase for trying such engines. Then NRF-A2, NRF-A3, CWE, or some more of these kind of engines which had tested. There's a long list of these such kind of testing which have been done. Some were failed, some were success, but we stopped testing these after 1972. I've taken two programs into consideration. Like first one was the rover program, and the second one was the NERVA program. Both the rover and NERVA program were technical successes. The decision to terminate the programs in 1972 was made on the basis of the public policy choices and not on the merit of the technology. We put the merit of the technology aside and we went through the public. But we need to educate the people. That's what we could do now, because fuels will not be able to do. The results of these programs were to demonstrate that a nuclear thermal rocket engine could be developed to meet the objectives of structural integrity, restart capability, predictability, controllability, and reliability. At the program end, NERVA 1 design was produced, would have met the program objective, but that was never tested. These are some of the potential applications of a nuclear engine. A chemical rocket using liquid hydrogen and liquid oxygen requires 10 kg of propellant for 1 kg of payload. The nuclear engine requires 2.4 kg of propellant for 1 kg of payload. But an ion thruster requires only 0.73 kg of propellant for 1 kg of payload. But this doesn't mean that we can use ion thruster into our engine engines, because the advantage of nuclear rocket is intermediate between the chemical and ion thruster. When only exit velocity is considered, we can opt for ion thruster, but thrust generated by the ion thruster engine is very less. It is just a fraction of some newtons. But the thrust, an ion engine can only generate a thrust of fraction of newtons, while a nuclear engine can generate thrust of 200 kilometers. So it's better to go for a nuclear engine so that we can get better thrust and better speed. Firstly, as I've already told you, we had stopped testing these engines in early 1970s due to public policy and public opposition and some international treaties. So, but fuel will not be available and there are no other alternatives. So we need to educate our public so that we'll use these kind of engines in our future. An area of particular concern for such development is the shape of the public policy. Certainly, nuclear thermal propulsion has technical challenges. Public policy, however, is perhaps the greatest difficulty facing the first to deploy such systems. One of the primary issues facing the development, testing, and implementation of this technology is understandably public perception. According to studies, a major source of study response fears nuclear power safety for almost 30 activities and technologies. The actual risk from nuclear power was significantly less serious than the common public perception. Visions of a propulsion system that could explode a mushroom cloud on the pad at Kennedy or re-enter the atmosphere and rain down radioactive particles in the public backyard must be countered with comprehensive education programs. These educational efforts must focus on providing accurate information concerning nuclear technology to counter effects the mass media distortion, accuracies of safety from the testing phase to disposal phase of spent propulsion stage must be made clear to the public. Specific applications of this guidelines, such developments need to be made in such a way that the public confidence in the technology is established.